look at some more examples of that. Let me go to the page here and see if I have some that I think I would recommend. Um, certainly, this I work hard. Um, okay, this one right here, this homework 6 problem 12, it covers everything. It's also long, 30, 40 minutes, but it's all in there. But if you want something a little shorter, let's see. Um, I don't see that I have one that's a little shorter, so I will put some more up when we finish tonight. I will put some. Well, let me just see if I can find some real quick. Y'all could go and watch the project videos from last semester. In case you haven't had enough of doing the 2742 project, I've got all the videos from last semester's project that you can go and watch. No? No? Let's see.
Would you say like the summary of like, the final would be based off of like, understanding sequences, counters, and basically like,
Sequence detectors, counters, and analyzing circuits, like what we
yeah.
just did. But also counters. I haven't done a counter today, but yeah. I did kind of, but I didn't. There's more with counters. But if remind me before we go, and I'll do another one.
Okay. Is there anything like, understanding like a Verilog code or some
Yes, that's
sort?
going to be in there too. So I'll try to get that as well.
Okay.
Um, okay, here is apparently on April 3. It looks like I did one, so I will. Let me take a quick look at this one. Okay, so yep. Yep. Okay, so here's another one. I'm gonna post this one. This is so our OR gate. This is an example of. So this is from homework 6. So it's another example of analyzing a circuit. So I'll post this in the SI resources. I do not know. I never actually seen an exam. So the only exam that I've seen is this one that I have from Dr. Trahan, but I've never seen one of his exams.
Our midterm wasn't 3 questions.
Yeah, it was 3 questions.
I imagine it'd be like 5. So, or like 9. Yeah. So it's actually so I like that. That's probably recommend right there. Yeah.
Okay, so
The problem that you had just did was that was an analysis.
that was an analysis. Yeah, and then I just posted another analysis that I recommend that y'all look at. And then if you have time to look at that, the problem 12. So, okay. What did I just say I was going to do? Sequence detector. Okay, so let's combine, let's see if we can combine two things at once. A sequence detector. He said that he went over this on the last class. He said attendance was kind of spotty at the last class, and he said there seemed to be some people didn't seem to understand it that well, and he also did the review session, and he suggested it was something that I go over. So,
Probably
this is going to be something that you'll probably have to do.
I was just hanging out.
I went to like the first hour of this review session.
So, construct the state diagram of a Moore type sequential circuit with input D and output G that behaves in the following fashion. When the input sequence is 0, 1, 0, 1, zero, 1, 0, 1, on the four preceding clock cycles, then on the next clock cycle, output G is 1. Otherwise, G is 0. Okay, so we want to see what it is that we're actually detecting here and what our various states would be. So it's trying to detect if the preceding 4 clock cycles looked like this, then it'll output a G. Output a 1. Otherwise, it'll output 0. So you want to think about, yes? You want to be thinking about what gets you towards your goal. What steps get you towards your goal? And so the first thing that you would have is our reset. And this can be equivalent to saying that the only thing you have going towards your sequence is 1. I can say those two things are equivalent because if to build up my sequence, I'd have a 0 and then a 0, 1 and then a 0, 1, 0 and then a 0, 1, 0, 1. And if all I have is a 1, that does not fall into any of these categories, so that doesn't help me at all. So that's one state. Another state that I have is if I just have a 0. That's another state that I have. I've got just a 0. I'm headed towards my goal, but I'm not there yet. Both of these would have an output of G equals 0. Okay, then another step towards my goal would be to have a 0, 1. And that would be G equals 0. And then my next step would be 0, 1, 0, and G equals 0.
So is each thing in each of, I guess, the states line up with in the column right there?
This is state A, B, C, D. No, yes. Well, let me call this state B, C, D, E, and state A was reset. And then I can call this A, A, B, C, and D. And then state E would be that I have my entire sequence, and that's when I would output a 1. But the tricky part is how do I get from one to another? Because it's not just going along. You have to see, based on my input D, where would I go? So let's say I'm starting here at my reset. If I get an input of 0, well, I had a 1, so I had a 1, but now I got a 0. Well, that gets me to my first step here. So if I have a D bar, that gets me there. But if I get another 1, I'm right back where I started. I don't have anything. And that's D. So for each of these states, I need to figure out what happens if I get, no matter what my input is. So if I'm at state 0, that means that I have a 0. So I don't really care about what else I have before the 0. I just have a 0. If I get another 0, I haven't advanced any, but I haven't lost any ground either because I still have a 0. So that's D0. But if I have 1, 0 and I get a 1, then that gets me to my next stage. So that'd be D.
How are you determining like what goes to where? Like I guess I'm asking like what is making you go from state to state?
My input D. And I'm trying, so I have possibilities for my D can either be 0 or 1, and that's my input. Now, what state I'm in depends on what I've already gotten. And so my state A says that what I have in my path towards getting my sequence is just a 0. My sequence that I'm trying to detect is 0, 1, 0, 1. That's what I'm trying to detect. These are my different steps along the way of getting there. So if I have just a 0 and I get another 0, what step am I on? Am I on nothing at all, which is that I have a 1? Am I on a 0 where I have a 0, 1? If I have a 0, 1, 0, or do I have the entire thing? I was at a 0. All I had was a 0. I got another 0. All I have is this. I'm right back where I started. But if I was at a 0 and I got a 1, then I have advanced to the next step because now I have a 0, 1.
Okay, so you're just saying like hypothetically.
What?
Like you're just talking about like hypothetically there.
No, I'm looking at every possible input. All I have is one input, it's D, so my only possible inputs are 0 and 1. And for every possible input, I'm saying what state do I go to based on that input. If I had 2 inputs, I'd look at all 4 possibilities. So now, given I've done both of my possibilities when I was in state B, now I'm in state C. State C means that I already have a 0, 1. So my two possibilities are that I get a 0 or I get a 1. So if I'm in state 0, 1 and I get a 1, then now I have 0, 1, 1. 0, 1, 1 is nowhere in my path of getting to my goal. So if I get a 1, I go back to the start. On the other hand, if I get a 0, I had a 0, 1 because I was in state C. I get a 0, 0, 1, 0. That brings me to state D. Now, if I'm in state 0, 1, 0, and I get a 0, that doesn't bring me all the way back to the beginning because I still have one step towards my goal. I still have that 0. So if I get a 0, I go to this stage. If I get a 1, then I've gone all the way back to my goal. I get all the way to my goal. But if I'm at 0, 1, 0, 1, and I get a 0, so I'm at 0, 1, 0, 1, and I get a 0. If I look at my last three inputs are 0, 1, 0. That's state D. So if I had, let me write this again, if I had a 0, 1, 0, 1, and I get a 0, then the last three inputs are 0, 1, 0. That's state D, so I would go back here. So that's if I get a 0. If I get a 1, however, if I had 0, 1, 0, 1, and I get a 1, then 1 or 1, 1, none of those are anywhere on my path towards getting the sequence, so getting a 1 brings me back to that state.
So how does, for state D, so you have 0, 1, 0, and if you get a 0, then you go back to state B. But state B is equal to 0, so how can 0, 1, 0, 0 be equal to 0?
0, 1, 0 is not equal to 0. 0, 1, 0 is, those are the last three inputs that I had. So my states are based on this. Okay, so the whole point of this is to detect when I have gotten this. When that has come up, then I output something. Now, I can be partway towards getting that goal. So I can have a 0, 1, which means I've done the first two steps, but I blow it if I then have a 0, 1, 1, because then there's no way my last 4 clock cycles are going to be 0, 1, 0, 1. Now, if I had 0, 1, 0, and I get a 0, there's no way my last 4 clock cycles are 0, 1, 0. You said, how can it be 0 if it was 0, 1, 0? My last 3 clock cycles are not 0, 1, 0. The only thing that is getting me towards having this sequence is that I have the first one in here. Because 0, 0, these two together, that's not in my sequence anywhere. The only thing that's in my sequence is this 0. Try and let me go. I think I finished this one for the state diagram, but let me give you another example. Yeah, so the state diagram is done. We didn't do, we did not design flip-flops for it. We'll do something like that in a minute. But let's do an easier one. So let's say, but that was a test question, not from Vedi, but it was a test question. So that's something reasonable. Let's say that your sequence detector is just supposed to detect 110 on the last 3 clock cycles. Okay, all of you, I'm going to pause the video. I want everybody here, everybody out there in Zoom world, to come up, draw a state machine that detects 110. What's that? No, we're not. I'm not giving you any inputs because the inputs. I mean, I could give you inputs. Okay. So I'm going to stop for a second. So let's say that that's a different question. So if I had this. And the problem says to output a 1 anytime the previous 3 inputs were 110, we might say, well, when would we have outputted a 1? So going along here, we would output a 1 right here, because we have 110 right there. We would output another 1 right here. We would output 1 right here, and right here, and that's it. Okay, but that's a different question. That is, given this set of inputs, when would you output a 1? Notice this one doesn't have anything where you would overlap. Like if I had 1010, then I might have that. If this is what I was detecting, I could output a 1 here, but then I could also output a 1 here. I don't have to get a whole another 4 clock cycles because I can reuse some that I've already had. All it's saying is the last 4 clock cycles are 1010. But that's a different question. So I'm not giving you any inputs. I'm just saying I want you to design the state machine. I want you to give the diagram that shows how it would do this. So what are the various states that this state machine would have? If y'all feel like you know you're not ready to do it yet, I'll just go ahead and start going over it. Or if y'all want to give it a shot, you can give it a shot. To go ahead and go over this unless somebody else wants me to check theirs before I go over it. All right. So I'm supposed to detect a 110. And so I'll start with my reset, which means I haven't gotten anywhere towards getting my 110. So the first thing I have to get is a 1, then I have to get another 1, and then I have to get a 0, and then I will have reached my goal. So if all I have is a 0, I haven't gotten anywhere. So this reset is the same as having a 0, and also my output is 0, whatever I want to call my output. So at this point, I have nothing. Got zipped, so I got nothing. But if I get a 1, then I have made it to this first step here. If I get a 0, I'm going back to this one. I will call reset, I'll call that A, and I'll call this one B, C, D. So now I'm at this stage where I have, this is stage B, where I have a 1. My output is still 0 because I haven't gotten my 3 clock cycles yet. But I have a 1. Now, if I get another 1, I've advanced to stage C. If I get a 0, then I'm all the way back to my beginning because 1 0 is not a sequence that I can use to build on. Now, if I'm in state C, that means I have a 1 1. Well, if I get another 1, I still have a 1 1, So if I get another 1, I come back to C. If I get a 1, 1, 0, then I win, because 1, 1, 0, that's the state I'm trying to get to. That gets me an output of 1. This one I had my output of 0. Now if I'm in state 1, 1, 0, and I get a 1, that brings me back to state B, because all I have is a single 1. If I get a 0, I go back to my reset state.
So how do you know like what number you're looking at once you get to the next state? Like how do you know if you're looking at like the last two or the last one or the last
It's how I defined my states. So I defined my states as A was nothing, B was 1, C was 1, 1, and D was 1, 0. So if I'm at state C, then my two possibilities are 1, 1, 1 and 1, 1, 0. And I want to look at these and see are, okay, so how far back do I go? As I want to get as much towards my sequence as I can. So for this one, I would use these two because that gets me all the way to here. For this one, I don't have anything, it takes me here. So I would look at both of them because that gets me farther ahead. Okay, so now let's take this same machine here, and let's now figure out how we would actually design such a circuit. So how many states did we have? I think I had 5 states, right? No, just 4. Wait, A, B, C, D, 4. Oh, good. Whew. Why? Why did I say, whew? Why is 4 states so much better than 5 states? No, not quite. It's just 4 equals 2 to the 2, and 5 is bigger than that, so the 2 to the 2, I can use 2 flip-flops. If I had 5, then I have to use 3 flip-flops. Because I have to have the number of flip-flops I have has to be able to accommodate all that I've got, and 3 flip-flops will accommodate 8, but I have to have all of them to do 5.
So if we did have 5,
We'd have a lot of don't cares. A lot of don't cares. So, I guess I probably should do that. I'll do an easier one with a don't care. So I'm not going to do the one we just did. Let's say all we want to detect is with the previous 2 clock cycles were 1, 0. So that's all we want to detect. So we have nothing, we have a 1, and we have a 1, 0. So this will be pretty easy to design. So this is also equivalent to having a 0. I'll call this state A, this state B, this state C. So if I had um, mm, so reset, and my output is 0, And I'm just going to put over here on the side because it helps me. That's equivalent to having a 0. Then if I get a 1, I'll go to state, so this is state A. I'll go to state B. That's equivalent to having a 1. My output is 0. If I'm at 1 and I get a 0, I go to state C. And then in that case, my output would be 1. Going back to state A, if I got a 0, I would go back to A. If I'm in B and I get a 1, I go back to B. Did y'all see that? And if I'm in state C, if I get a 0, that brings me back here. And if I get a 1, that brings me here. So A, B, C.
So is the reset, just the opposite of whatever the first state is? I wish it would, so like.
The reset is that, yeah, it's yes.
What does that do? Like what one do?
Okay. So now in this machine, I have 3 states. So how many flip-flops do I need? 2 flip-flops. 2 flip-flops. All right, so I'm going to have 2 flip-flops, and I can say that I've got my table. So present state, next state, output. My next state depends on my input, D equals 0, D equals 1. So I have A, B, and C. And from A, if my input is 0, I went back to A. If my input was 1, I went to B, and my output was 0. From B, if my input was 0, I went to C, and if my input was 1, I went back to B, and my output was 0. For C, if my input was 0, I went to A. If my input was 1, I went to B, and my output was 1. Now I need to write this with ones and zeros. And there's no rule for how to do this. If there had been more time in the semester, you might have learned some ways to kind of make it most efficient. So present state, next state, output. For lack of any reason to do otherwise, I'm going to call this A00, B01, C10. I do have to account for 1, 1. I have to account for every possibility. Now for 1, 1, I'm going to put in don't cares. for everything. Now, A was 0, 0. B was 0, 1. C is 1, 0. B is 0, 1. A is 0, 0. And B is 0, 1. This is little y0, little y1. This is big Y0, big Y1, big Y0, big Y1. Now we're going to do a Carnot map. Now what we are deriving is our excitation equations. So I'll do Y0. So for Y0, I have little y0, little y1, and D. So 0, 0, 0, 1, 1, 1, and 1, 0, and 0 and 1. And I'm looking at y0, and y0 is this first column here. And in this box right here, or this column that I'm outlining, that's when D is 0. So that's my top row right here. So when D is 0 and little y0, little y1 are both 0, y0 is 0. When I have 0, 1, and D is 0, y0 is 1. When I have 1, 1, I have a don't care. And when I have 1, 0, I have a 0. Now, when D is 1, that's the second column over here. It's 0 everywhere except for 1, 1 that is a don't care. And so the best way to get this one is right here. And so I will say y0 equals y1 d bar. Now I'll get y1. So I'll do a Carnot map for y1. y0, y1, and d. Okay, when d is 0, there's all zeros except for 1, 1, which is a don't care. And when d is 1, they're all 1s except for 1, 1, which is a don't care. So y1, gets this bottom row, y1 equals d. Now let's do our output. Our output was just based on y0 and y1. And when y0 was 1 and y1 is 0, that was a 1. y0, 1, and 1, 1 is don't care. And so our output will be y0. All right, so now I have these excitation equations. The easiest way to design a circuit like this is to use D flip-flops. If you want to make things harder on yourself, you can use another kind of flip-flop. But D flip-flops means I can just use these equations. I had two flip-flops. This is y0, y1. I will have a clock. And y0 is, and I have an input D. Y0 is the AND of not D and Y1. And Y1 is simply D. And my output is Y0. And that would be my circuit. I could very easily see a question like this being on your test. Yes,
For Y1, how did you get the truth table again?
for Y1. Right here?
Yeah.
Okay.
Which part of the truth table?
Okay, so I looked over here at my next state, and Y1 is this, the second column of each of these. And so this, this tells me Y0 and Y1 right here. So when Y0, Y1 are 0, 0, and this right here, D is 0 for all of these. And so my top row with D equaling 0, those were all 0, except for the 1, 1 that was a don't care. And then over on the other side, that was where D equaled 1, they were all 1s.
And then for the output, how did you? It's just a two variable.
It's just two variables, and so, and it only depended on the state. And when y0 was 1 and y1 was 0, y0 was 1 and y1 was 0, it was a 1. When they were both 1, it was a don't care.
So D not is 0, right? And D is 1.
Say that again?
D not is, or like D bar is 0, right?
Yes.
So, because I didn't initially, like, I did like 0 and 1 for the transitions
Uh-huh.
between states. So could I have just said like on an exam, could I have just said like capital Y not equals, or like capital Y0 equals little y1 and 0?
Nah, you need to give it a name.
Okay.
Yeah. It seems like it would work the same, but you're going to want to say what the input is.
And then what did you do with D in the circuit? Like when you drew the circuit, what did you? If it was a D.
D was an input. And so where I had not, so Y0 is, that's my excitation equation for my D0 and D1. And it was Y1 and not D. So I put a little bubble here for the not D and Y1 coming around, and I've got the and of those. And then Y1 is D, so that's just the input into this one.
Is D don't? That's not don't care, right?
No, no, this is, I'm sorry, is my input. I don't know why I used D as an input. It was because somewhere along the way we had a problem that had D as an input.
Okay.
Yeah, so this is input.
So the D's in the truth table are,
Yes,
and G is your output.
yes.
And you got each of the time maps of each of the excitation equations from your table, right?
Yes. And what's the hard part about this for me was realizing that my Y0 consisted of these values and these values, and my inputs were over here, and then also whatever my input was up here.
And then, so you got your output, did you get that from the table or from your state diagram?
Yes.
Okay.
Well, I got my table from my state diagram. This came from my state diagram. The big thing that changed from here to here was adding my don't cares.
So
Okay.
if you had like 5 states, then your last one would just be state?
Now, if I had 5 states, I would have to have 3 flip-flops, and I would have 0, 0, 0. I could assign any one of them to be the states that I mean, I don't have to do them in order, but I do have to account for all of them.
Like it would, like those last three lines would
All be don't cares. Now, it does not actually have to be the last 3. You could say, I want this one, and this one to be my don't cares. It doesn't matter, but yeah. 3 of them would be don't cares. Okay, let me stop this.